can't see the recorder. So let's see if I can get the current slide open now. There we go. Finally, it showed up. Okay. All right. So you say no questions, no issues, no concerns. All right. I had hoped more people would be here by now. I was beginning to wonder if I'd even sent the thing properly, but I'm glad you're here. You indicate that the invite did go out and it got posted correctly. But I'll probably say it every time someone new comes in, but I may forget. But if they listen to YouTube video, they'll hear it. Do you know what Wednesday is? Veterans Day. And the state of Alabama, unlike a lot of states, Alabama counts Veterans Day as a state holiday, which means school is closed. No classes, no nothing, okay? So we won't be having class on Wednesday. So what we're going to do today, that's it for this week. Now let's look ahead a little bit further. Next week, we have class Monday and Wednesday, of course. And then the following week after that is Thanksgiving week. Now, I'm pretty sure, I know in the past it's always been, that students have the whole week of Thanksgiving off. Have you heard any differently this year? No. Okay. We still have to work Monday, Tuesday, and Wednesday, but it's professional development type stuff. So we have class today, no class Wednesday, class Monday and Wednesday of the following week, no class the week after that, the Thanksgiving week, and then we come back after Thanksgiving week and have one more week of class, and then we have final exams. So that last Wednesday, that first Wednesday in December, after the end of that class, then I'll be giving you your final exam, and you'll go from there. So we are on the short rows now. There's not much left. One class this week, two class next week, two class after Thanksgiving, and then final exams. So is that how you understand the schedule as well? Okay. All righty. Well then, and I think you're already pretty much on top of things as far as getting research papers in and tests in. I can't remember now because you're in 3 classes. I can't remember if all of them are in, but be working on those because those it's going to come sort of fast and furious at the end now. So be sure to get that done. All right. Any questions or issues raised from any of that? Okay. All right. Well, where we left off last time, we started in chapter 12, vector valued functions. And I'm pretty sure I put test, I don't remember which number test it is. The chapter 11 test was posted, and hopefully everybody has seen that or worked on it. I know at least one person, because one person had some questions on it, so I know it got transmitted well, at least to some. Were you able to read everything on it, or were there any issues with that? Oh, okay. All right. Let's see. I just have noticed that I need to scoot us over a little bit there so I can see my screen better. Okay. So where we are now is chapter 12, vector valued functions. And section 12.1 is also named vector valued functions. We did example 1 last time. Now, I apologize for my voice ahead of time. My wife's parents have been pretty much trapped inside their house because of COVID and stuff like this, and they were just so anxious to get out of the house, and they had bought a place down on Smith Lake early in their marriage, I think, or after they moved to Huntsville anyway, and we've been taking over the responsibilities for it because they're in the mid-80s, and they said, please, let's go to the lake this weekend. So we hosted them there, and I worked most of the weekend burning brush and doing things like this, and it's gotten me so congested that I'll just break out sneezing every now and then and other stuff. And then too, I got totally exhausted this weekend too. I probably shouldn't have done as much as I did, but I felt like I was getting stronger, but then sure enough, not. So sorry if I crack up in the middle. So hopefully I won't do too badly. So example 2 is where we're beginning today. It's both on the slide set and it's also located at larsoncalculus.com. You can see an interactive version of this type of example. So it says sketch the space curve represented by the vector value function r of t is equal to 4 cosine ti plus 4 cosine sine tj, and t goes from 0 to 2 pi. Okay. Now, just to remind ourselves, when it's bold like this, that means it's a vectored value function. Your independent variable is t here. That's a scalar. Okay. These are scalar functions. 4 cosine t is a scalar function. 4 sine t is a scalar function. T is a scalar function. Okay. And the t varies from 0 to 2 pi, but the components of that vector, sorry, the components themselves are scalar values, but they're in the direction of the I, J, and K vectors. Okay. Now, if I don't know if you can hear it or not, but my dog's downstairs barking like crazy. I think it's the neighbor's cat comes over and teases her. The dog's inside, the cat's outside, and the cat just loves to sit outside the door and bother the dog. Okay, so they've got a little thing going. Okay, hopefully it's not too distracting to you. All right, it says sketch the space curve. Well, unfortunately that means I have to try to draw a three-dimensional curve on a two-dimensional screen here. So we'll make this the x-axis, that the y-axis, and this the z-axis. I may extend this up a little bit. Okay, now let's start where it begins here. T is equal to 0. Well, when t is equal to 0, cosine of 0 is 1. 4 times 1 is 4. And that's on the x-axis. So there's 1, 2, 3, and 4. We'll go 1, 2, 3, and 4 on y, and we'll go 1, 2, 3, 4, 5, 6, 7, 8 on z. I don't know if we'll need that much, but we'll try. Okay, I think somebody's coming in. Jemanuel's here. So let me mark him as present, and we'll go from there. Okay. All right. Welcome, Jemanuel. Can you hear me yet? Jemanuel, are you there yet? Okay. You just got muted. Can you hear me? Jemanuel, can you hear me? Okay. I can't tell if you can or not, but let me make the kind of important announcement. Don't know if you know what Wednesday is, but Wednesday is Veterans Day. Now, what does that mean? Well, in Alabama, Veterans Day is a state holiday, which means the college is closed. There will be no classes, no administrators, nobody doing anything at the college. So just for your acknowledgement, you know, we will not be having class on Wednesday. Sorry about that. Bad news, I know. All right, and we were just sketching this graph. I tried to draw a three-dimensional graph here on two-dimensional plane. That's kind of hard to do, but here's the graph. Okay, here's Kyle. Good deal. So Kyle is here as well. Let me get him marked present. Okay. Kyle. Okay. Okay, Kyle, can you hear me?
Yes, sir. Sorry, baseball ran a little long ago.
I see, no problem. Just wanted to let you know, can't tell if Jermanuel can hear me yet or not because I haven't heard from him, but Wednesday is Veterans Day. Did you realize that? Don't know if you.
Yes, sir.
Okay, and you also know that means in the state of Alabama, that's a state holiday. So there will be no class on Wednesday. Just wanted you to,
Okay, yes, sir.
yeah. Sorry about that. I know it's disappointing. Okay.
I'm gonna miss you.
Oh, yeah. Wipe it off. Wipe it off. Okay. Now, also, I mentioned this to Kara before you or Jermanuel came in. Let's look ahead a little bit, and things are getting awfully tight here because there's class today, no class on Wednesday. Then next week we have class Monday and Wednesday. The week after that is Thanksgiving week, and my understanding is there are no classes for students at all on Thanksgiving week. We have professional development Monday through Wednesday, but students don't have any classes during Thanksgiving week. So you have the whole week off. Then there's a week after Thanksgiving. I think that's the first week in December. We have class Monday and Wednesday of that week. And then on Wednesday of that week, the first Wednesday in December, I'll be giving you your final exam, and you get that back into me by during the following week, which is final exams week. Now, I'm guessing that most of you, maybe not all of you, but most of you are getting awfully close to graduating. Is that right? If you are graduating this term, fall term, then that means that the odds are, I don't think they need your grades super early, but you might be a little more pressed for time than the other students are, just because, but I don't think it's a big issue, not with COVID and stuff, because it just doesn't seem to be a problem. So anyway, just to let you know, the stand by for that. Watch out. Are are they talking with y'all about graduation or anything? Virtual graduation? I don't know how they're going to do it. I'm sure there's something planned. I just haven't seen all the emails. Probably I'm behind in emails because we were out of town this weekend and we were someplace where internet was almost zilch. You could barely get a phone signal there. Okay, but anyway, just to let people know. Here's example 2. We're in chapter 12, vector value functions. In 12.1, the first section is named vector valued function. Okay, we're on page 821, example 2, and this is also located at larsoncalculus.com. You can see an interactive version of this type of example. So, to follow up with that, here it says sketch the space curve represented by this vector value function. Okay, t, let's start with t equals 0, the smallest value here. Okay, cosine of 0 is 1. 4 times 1 is 4. So we come out 4 units on the x-axis, because that's the I is your unit vector along that. So 4 here. Sine of 0 is 0, so you don't go out any direction on the y-axis at all. And then 0 times k would be nothing on t. So here you are. There's where you start, right there at that point. Okay, let's go to the next convenient location. How about t equal pi halves? Okay, so that would be 4. This will be r of pi halves. You could do intermediate ones if you want to. These are the easy ones. 4 times the cosine of pi halves, I, plus 4 times the sine of pi halves j plus pi halves k. Okay, well, cosine of pi halves is 0. So 4 times 0 is 0. Sine of pi halves is 1. 4 times 1 is 4. Okay, so down here, this is where you'd be. 0 on the x-axis, 4 on the y-axis, but then your pi halves up on the k-axis. Well, pi is just a little bit more than 3, so you're going to be somewhere just above 3 halves, or 1 1/2. So there is approximately where you're going to be on the, you're above this point right here in the z, above that in the z-plane. So, sorry, I was explaining to Kara, we were at the lake. My wife's parents wanted to get out of the house, you know, this weekend, so we hosted them at, they had a place at Smith Lake that we're now responsible for, and we had them there, and we had a good time, but I was worked probably a bit too hard there, and also burn brush, so I'm all congested and that kind of stuff. So anyway, this is starting here and moving around and basically following a circular pattern here, but also climbing slightly to reach that point somewhere there. Okay, well, let's take the next most convenient place. T equals 0 here, t equal pi halves here. Let's have t equal pi. Okay, so r of pi is equal to 4 times the cosine of pi I plus 4 times the sine of pi j plus pi k. Now, cosine of pi is -1. So now we're going to have to come back here on a two-dimensional plane and try to get a third dimension in here. Already had trouble there, and one here. Now the good news is the z is never negative, so we don't have to go down there any. So we're going to go back here, -1, -2, -3, -4. So we're starting here. The sine of pi, of course, is 0 again. So we're nothing in the y direction. And then we're up pi units, which is just over 3 units in the z direction. Well, so you just have to imagine 1 unit, 2 units, 3 units here. So this keeps climbing back over the y-axis, or the x-axis, the negative x-axis here. Now, I probably don't have enough curvature in that, but this is so hard to draw on a 2-minute. Drawing anything is tough. Okay, there's pi. Let's now move to t is equal to 3 halves pi. So r of 3 halves pi would equal 4 times cosine of 3 halves pi in the I direction plus 4 times the sine of 3 halves pi in the j direction plus 3 halves pi in the k direction. All right, now this is going to get progressively harder to draw. Okay, now cosine of 3 halves pi is 0 again. So you're not going, I'm sorry, is a -1. Cosine of 3 halves pi is -1. So we're over here in the minus, if I can find my pen, there it is. Okay, -1, -2, -3, -4. So we're somewhere over here. Sine of 3 halves pi is 0 again. So you're not anywhere in the X direction here. I think I've done this backward. No. I said it right the first time, drew it wrong. Cosine of 3 halves pi is 0, so we're 0 in the X direction. Sine of 3 halves pi is -1, so we're over here in the Y direction, and the J direction, and then we're up 3 halves pi. That's a little bit more than 9 halves pi, so a little bit more than 4.5. So there's 1, let me count them here, 1, 2, 3, 4.5 would be somewhere right about there. Okay, so this keeps climbing. Now it doesn't look like it's climbing much, but it is climbing to here, and then finally are at 2 pi, and that's the last value we have here, are at 2 pi. Oh goodness gracious, how did that get over there? Let me erase that extraneous mark. Okay, now I can't find my, well, that's not extraneous yet, is it? There it is. Okay. Okay. This will be 4 times the cosine of pi in the I direction plus 4 times the sine of pi in the J direction plus pi, 2 pi, I'm sorry, these are 2 pi's here. Okay, plus 2 pi in the K direction. Okay, so let's pick up again. Cosine of 2 pi, whoa, here comes a phone. Okay, and I don't recognize the number, maybe some of you do. Who's the phone number that just came in the room?
Hey, it's Esther.
Oh, hi Esther, welcome. Okay, so we got half the class here now. The top half of the alphabet is 3 out of 4. The bottom half is poor old Emmanuel holding it down by himself. So hopefully the others will be coming in. And Esther, I'll say this again for your benefit as well as the others. Do you know what Wednesday is? Veterans Day. And in the state of Alabama, Veterans Day is a state holiday, which means everything state related is closed, which means no classes on Wednesday. Sorry about that. I know that's disappointing. Okay, so there's no class on Wednesday. Next week we have a full week of class, Monday and Wednesday. The week after that, though, is Thanksgiving week. And if my understanding's correctly, there are no classes during Thanksgiving week. I know that's always been the case in the past, but we haven't always had COVID in the past either. So there are no classes during Thanksgiving. Then we come back for one more week. That's the first week in December, and we have classes Monday and Wednesday. And then on Wednesday of that first week in December, I'll be giving you your final exams, and you'll just need to get that back into me by sometime the next week. Now, if you are graduating this term, I know some of you are, you might need to check with the registrar's office or somebody and find out when you have to have your grades in. I don't think with COVID there's any restriction there, but I know back when we used to be on campus, they wanted graduating students' grades in sooner than non-graduating, but I don't think it really matters that much with COVID, but we'll see. Find out from them. Okay, so let's move on. We're in chapter 12, which is named Vector Value Functions. We're in section 12.1, which is also named Vector Valued Functions, and we're doing example 2, which is on the slide set, but it's also located at larsonscalculus.com. You can see the interactive version of this type of example, and we're doing it here. And this is really messy because you've got three-dimensional drawing on a two-dimensional plane. It's really hard to see it well. I'll show you their picture if you can't see it in the book now. Okay, we're just had listed the function at t is equal to 2 pi, which is the last value they gave here. If I could get my pen to show up. Where is the pen? Okay, I can't see it anywhere here. There it is. I found it. All right. So when when t is equal to 2 pi, this is 4 times the cosine of 2 pi. And I think we just lost somebody. Cosine of 2 pi, of course, is 1 again. So this will be 4 here on the x-axis. Sine of 2 pi is 0, so you won't be anywhere on the y-axis. And then 2 pi is about 6. Okay, so we go up about 6 units from here. 1, 2, 3, 4, 5, and 6. Somewhere here. And this comes around back here. Now we got somebody, oh, Cal had to get punched out and then back in. So I've already got Cal here. Sorry about that. He's still connecting to audio.
Sorry, my thing messed up.
Okay. All right. Now this is a pretty ugly drawing. Okay. Let me show you in the book what this is. Okay. And I can't draw them this neatly in the book, but this is what you call a helix. Now, they took advantage of being able to do a little bit better of a orientation of their axes, but that's basically what you're seeing here. It's basically a tin can, a right circular cylinder that you're climbing with the helix. Okay. And again, my drawing is really, really lousy, but this is what we've got. Okay. And this is a circular base. Okay. And you're going up the tin can around the axes like that. Okay. And that figure is called a helix. Let's see how much they show of it here. I was holding up the book, but I bet you for some reason, there we go. They're covering up my, okay, let me erase my drawing and let you see how they do it. From the first two parametric equations, x equal cosine t and 4 times cosine t and y is 4 times sine t, you can obtain that by squaring both sides of both equations to get x squared plus y, and adding them together is equal to 16 times sine squared plus cosine squared. That's just 16. That's a description of a circle. So you have a circular base as if you had a projection of a circle on the xy plane. Now, that means that the curve lies on the right circular cylinder that goes above the xy plane. Now, to locate the curve on that cylinder, we use the third parametric equation, z is equal to t. That starts at 0, goes up to pi halves over on the positive y-axis, up to pi on the negative x-axis, over to 3/2 pi on the negative y-axis, and then up to 2 pi again, which is around 6 on the z-axis. So that's what's happening on z. You're going around the tin can, circling your way up. Here's the figure. Note that as t increases from 0 to 4 pi, now where did they get the 4 pi? Okay, unless I misrepresented the problem, and I don't think I did, the point spirals upward. So this is not the drawing they had. They had just one time around from here to there, and then back right to here. They just happened to draw one more circle around to get them up to here. But you see, the one we had only went to t is equal to 2 pi. So I don't know why they drew this one, except to show that helix a little bit better. Because that one time around, it really does leave you a little confused of what's happening to that. It doesn't look like it's going around. Go around the second time and you get a little bit better idea. So they drew it 0 to 4 pi, even though the problem was only 0 to 2 pi. Okay. Don't know why they did it, but they did. They did it in the book, and they did it. Oh, I see. In the book, they have it right. I see. In the book, if I can find my pen, I see. Their problem in the book was, well, I got to find the pen again. There it is. They put a 4 pi here, not 2 pi. So I drew the one they gave in the book. They, evidently, the graphics person who did the PowerPoint messed that, okay? And he just put 2 pi there. So it is a little easier to see. Of course, that would have really gummed up our works the way I drew it to begin with. All right, any questions on that one? Okay, now I see why they went to 4 pi. Their slide didn't say that, but the book did. Okay, a real-life example of a helix is shown in this drawing. This is actually a double helix. I don't know if you've recognized this or not, but in 1953, when I was just 2 years old, Francis Crick and James Watson, I think they're both from Britain, discovered the double helix structure of DNA. This is what determines who you are, okay? They have certain of these pairs that go, there's one helix on one side and one helix on the other side, and the DNA strands basically go between these, and depending on what characteristics they are transmitting, that determines like your hair color, your handedness, your height, your weight. I mean, it just determines just about everything about you. That's your structure of the DNA. That's a double helix, one going around, the other going around as well. And I mean, for years people were trying to figure out how in the world that thing was structured, and Crick and Watson discovered that. All right. Now, they are skipping examples 3 and 4, so let me get my pad back again before we get to limits and continuity here. So let's go to the whiteboard. Almost called it the white sheet. And let me do some more housekeeping here. You can't see it, but there's a toolbar, taskbar right in the way for me. And then with your names in Zoom right there, try to get as far away from that as possible too. You can't see it, but it does block my ability to write. Okay. It says represent this parabola. This is example 3, top of page 822. Y, oh, I'm not on, okay. Somehow I lost the screen share. Okay, let me get it back. It was there. When I looked down, it was gone. I mean, look back up, it was gone. So here's this thing. Y is equal to x squared plus 1. Oops, I say 1 and write y. I don't know why. Okay. Okay. Represent that parabola by a vector valued function. Okay, now, first off, as if this wasn't going to be strange enough to begin with, here's the thing. There's an infinite number of answers. You can represent it in an infinite number of ways. Okay, so don't sweat that. I want to do the easy way. Okay, and here's my easy way. Let's pick the most complicated variable here. To me, that's obviously the x variable because that's the one squared. Y is just sitting there. Okay, so let's just let x equal t, our common parameter t. Then y would equal t squared plus 1. There we have it. There's our vector value function. Well, we don't quite have a vector value function yet. Let's write it as a function now. R, the vector R, as a function of our favorite variable t, is equal to the x is ti plus, and y is t squared plus 1 j. There's your vector value function. This thing is such a pain in the neck. Okay, my house top here disappeared. Okay, there we go. There is your vector value function. Okay, they did it of t. You can name that anything you wanted to. That's not the only one. It's one of, like I said, an infinite number of ways you can express that vector value function. Okay, any question on that? Easy way to do it. Okay, let's go to example 4. Any questions before I clear this? Well, I'm trying to clear. Okay, there we go. All right, let me get the book back in the lap so I can read it better. Sketch the space curve. This is example 4. X squared over 12 plus y squared over 24 plus z squared over 4 is equal to 1. Okay, now we're going to also hold this to the fact that z, if I could write a z, has got to be greater than or equal to 0. It doesn't have to be, but they're giving us that. Okay, wait, I didn't finish reading. Sketch the space curve C represented by the intersection of this semi-ellipsoid, and that's why I'm going to go on and erase this, because that is pretty ugly. Okay, this is a z is greater than or equal. That's why they call it a semi-ellipsoid. So the intersection of that semi-ellipsoid there, where z is greater than or equal to 0, and the parabolic cylinder, and remember a cylinder, y is equal to x squared. This is one of my favorite things to do of all time, is sketch these space curves on a two-dimensional surface. That's just so much fun. And then it says, then find a vector value function to represent that graph, that space curve C as a graph. Okay, that actually I think is easier than what they're asking us to do here. So it says, first sketch the space curve C represented by that intersection. Okay, so here is going to be, if I can find my cursor, come on, show up, pen, wherever you are. There we are. Okay, so we'll come down here and go over here, and here comes Houston. Good to see. Hold on just a moment, folks. All right, the top half of the alphabet is perfect attendance, and poor old Jemanuel's at the bottom part of the alphabet holding it all by himself. Okay, love to have the other two here. Okay, 3 here, I guess it is. Okay, Houston, we're in chapter 12, which the title is Vector Value Function, in section 12.1, whose title is Vector Value Functions. We're on page 822, near the middle of the page, example 4. Okay, and here's what it is. It says, sketch the space curve C represented by the intersection of the semi-ellipsoid, and this is your semi-ellipsoid here, if you didn't recognize that already, and the parabolic cylinder, y is equal to x squared, that one. And we just have drawn the axis, so we haven't even started here. Now, before we get going too much, let me also mention to you what I mentioned to the others, because I don't want you to turn out being not understanding things that the others have heard. Okay? And here's what it is. Do you know what Wednesday is? You're absolutely right. And in the state of Alabama, unlike most states I've lived in, Veterans Day is considered a state holiday. Okay, which then means, of course, much to your chagrin and disappointment, will be no class on Wednesday. The college is closed. We are not offering classes on Wednesday. Sorry about that. Get over it. Okay, now, which means, of course, we only have class today, this week. Next week we have classes Monday and Wednesday. The week after that is Thanksgiving week. And unless things have changed significantly, students do not have any classes on Thanksgiving week. We have professional development Monday, Tuesday, and Wednesday, and then of course the college is closed on Thursday and Friday of Thanksgiving and the day after. And then we come back the week after Thanksgiving and have classes Monday and Wednesday, and then after that is final exams week. So that means on Wednesday, that's the first Wednesday in December, I'll be giving you your final exams, and they have to be submitted sometime the next week. The earlier the better, but get them in sometime that next week. In addition to that, there was something else I was going to say. Oh, research papers. They're due by that Wednesday, the first Wednesday in December. So if you haven't gotten those done yet, you have to have them done by that first Wednesday. Otherwise, you start losing points. Now, if you get them done this month, the month of November, you get that last little bonus points that's out there. If you turn them in that first week in December, Monday or Wednesday, you get just your score. If you turn them in after Wednesday, you start losing points, minus points. So please get those in sooner rather than later. Also, try to get all your other tests in sooner rather than later. Now, I'm a bit behind in getting them graded. I took them to we had to host my wife's parents at the lake this weekend because they had a place there. We're responsible for it now. But they wanted to get out of the house and to the lake, and we had a good time, but I worked probably a bit too hard with my anemia and also was burning brush, so I'm sort of congested today, so sorry about that, but we'll try to get over that too. But anyway, if I sound sort of congested, that's why. All right, so we're doing example 4. This is on page 822. Chapter 12, Vector Value Functions, 12.1, Vector Value Functions, and this also, well, here is your space curve. Well, we're getting ready to draw it. Let's first draw the semi-ellipsoid. What makes it semi-ellipsoid is the fact that it's only positive values for z. Okay? What makes an ellipsoid is that all of your variables are squared. Okay? And all the variables have plus signs in front of them. Okay? Now, this is not quite standard form. It's close, but not quite. Okay? If I were to write that in standard form, in my standard form, that would be x squared over the square root of 12. If the pen would work, squared. Okay? Plus y squared over the square root of 24 squared. I know that looks messier, but there's a method to the madness here. Plus z squared over 2 squared. Okay, because I know the square root of 4 is 2, and that's equal to 1. Now, why did I do that? Okay, you have no clue, do you? Okay, why would anyone do that? Here is the negative y-axis. Here is the negative x-axis. Going somewhere back here like that. Okay, we don't need negative z because z is restricted to be positive. Let's tick off a few points here. One, going to do y first. 1, 2. This pen is just not working well today. I have to just slow it down to get it to work. And up here we'll go. Now, we don't need all those 6 points, but we got them. All right. Now, why did I do that? Why did I write it in this weird form like this? Well, the square root of 12 is something in between 3 and 4, right? Because 3 squared is 9, 4 squared is 16, so it's somewhere in between 3 and 4. So 1, 2, 3, and 4. Let's just put it somewhere out here. May not be right, but somewhere out there. And the minus of that would be 1, 2, 3, 4, somewhere in between here. So somewhere here. So this is where it's going in the positive and negative x direction. The square root of 24 is very close to 5. Okay, so that's going very close to 5 here and very close to negative 5 there. And in the z direction, this is going up to, exactly up to. We don't do the minus because the z is always positive. Now, what I'm going to do next is try to draw that base curve. And this is laughable to see me try to draw this. But this is something coming out here, coming around here, going out to there, going around to here, and coming back around here somehow. Okay, that's supposed to be the ellipse at the base of this ellipsoid. Okay, now from there, let's try to draw this curve here. And obviously I don't have my scales done well. Okay, it's going like this and it's going like this. Okay, something like that. These are semi-ellipses. Okay, and then they go around. The ellipse gets smaller as you go up. They get smaller as you come out here, semi-ellipses. But that's basically what it's looking like. Whoa, that took off in the wrong direction. You have, these are almost half of a football, not quite, you know. These are coming out really poorly. So that's not helping a lot. Okay, now let's do this base here. Y is equal to x squared. Okay, well, obvious y is always positive for this. X can be positive or negative. So this is a, let's just draw the base down here. When x is 0, y is 0. So we're right there at the origin. When x is 1, y is 1. When x is negative 1, y is 1. When x is 2, y is 4. I don't know if that's going to fit on here, but let's just imagine that it does. So here is that that parabola that's on the base down here. Now, of course, it's not on the base. It's up here, and it comes down the ellipsoid here and goes down the ellipsoid there. So that's basically the curve that we're trying to draw. Okay, so this is the curve C. I know it's ugly. I know it's terribly ugly. Okay, but that's the curve we're dealing with. Okay, someone has his microphone on. I think it may be Esther, and there's getting to be a lot of static there. Esther, can you turn your microphone off? Okay, no problem. Okay, I was just hearing a lot of scratchiness. Okay, now, if you want to see what this curve should have looked like, there it is. Okay, and you see it does come up to the peak there, goes in either direction. I don't have the curvature going down the way it should, but you get the general idea. So that's supposedly the drawing. I really detest drawing these things, okay? But the second part of this says, then find the vector valued function to represent the graph, okay? Now, if you do anything like we did before, and some of you came in after what we did before, we let the most complicated part of the equations be your t, the parameter for the vectors, okay? And right off the top, I would say let x equal t. I don't know if I'm going to stay with that or not, but let's try that. Let x equal t, okay? Now, both of these have to be met simultaneously, right? This has to be true when that's equal to is true. Well, we can see from this that we would have, if that x squared is the same as this one, so this would be y over 12 plus, well, let me pause a moment here. Let's get it into t's. Why don't we do that? So let me go back and erase that. I think it would still work okay, but let's go on and try to get the parameter in here. Okay, so what we have here, if this would be then t squared over 12 plus, if y is equal to x squared, x is equal to t, then x squared would be t to the fourth, right? If you square t, no, is that right? Y squared would be x to the fourth, and that would be, so this would be t to the fourth over 24. Now, plus z squared over 4 is equal to 1. So by choosing x equal t, then you know this is t squared over 12. If you squared x, made x squared, that would be t squared, and then this would be t squared squared, okay? So y would be t to the fourth, okay? Because you're squaring then the y. So you have that. So now you can solve this for z. Okay, so what I'm going to do is multiply by our least common denominator, which would be 24. So I'm going to multiply everything on both sides of the equation by 24, and that would give me 2t squared plus t fourth plus 6z squared is equal to 24. Okay, solve for z. So that would give us 6z squared is equal to 24 minus 2t squared minus t to the fourth. Okay, let's divide everything by 6, and we get z squared is equal to 4 minus 1/3 t squared minus 1/6 t to the fourth. Okay, and then take a square root of it. Okay, so z would then be equal to the square root of 4 minus t squared over 3 minus t to the fourth over 6. Now that's one rendition of your parametric equation. Is that the one the book used? I don't know. Let's just see what they did use. Wow. Yeah, they said x equal t, y is equal to t squared. I didn't write it down that way, but I said it. Y is equal to t squared because y is equal to t squared right there, okay? And z is equal to, and they wrote it differently. They wrote it as a fractional form, so let's see if they squared it right. If I could get my pen to show up, there it is. Z is equal to, now they do the square root here, and it's only positive. That's, remember here we said z is always greater than 0, so we don't need a plus or minus there. And they divided everything by 6, okay, and that would have given them 24 minus minus 2, is it? Let me see, my brain's not working well. Yeah, 2t squared minus t to the fourth, okay, alright, that's what the z would have been, but they went one more step and factored that to be 4 okay, put a t squared here and a t squared there. One of these is a minus and one of them's a plus. I think, nope, got it backwards. That's the plus and this is the minus. Nope, yuck, this thing aggravates me no end. Okay, let me erase. Well, now my eraser's not working. Okay, let me get this one more time. Okay. Alright. This is a plus t to the fourth. This is a minus t to the fourth. Okay. The square root goes down into the denominator here too. And this would be 6 here and 4 here. This all over 6. Okay. Got it. Now, they said find the vector value function. So this gives us my x, my y, and my z. So the vector value function, if I could find it here, r as a function of t for this curve right here would be equal to ti plus t squared j, that's your x and y, plus the square root of 6 minus or plus t squared. Those are squareds, they're not fourths. They started off being squared. Plus t squared times 4 minus t squared over 6. K. There is the function, and I think that's how they have it. Ti plus t squared j plus the square root of 6 plus t squared times 4 minus t squared over 6k. Now, there is some limitation here of what values the t can be. Okay? And sometimes this is a bigger, harder thing to do than what we just did. Here we know that t has to go from, because on the x-axis here, that goes from the square root of, let me see if I can get this right. If you were to square that, oh yeah, okay, I was looking at the wrong thing. It's going from here to there, and you have to kind of figure out what your x value is here. We don't know the x or the y here per se, but we do know the z is equal to 0. So for that to be true, yeah, here we go. For z is equal to 0, let's see, how's the best way to show that? Okay. When I was drawing this, and there's no guarantee I was drawing it right, I was aiming for this to be, well, just by looking at it, it looks like it's pretty close to a 2 here on x and a minus 2 here on y, on the negative x. Let's see if those do hold up. If you put x equal 2 plus or minus 2, that would be 1 over 3 plus, and the y then, we know if x equal t, that would be 2, so this would be 2 squared over 24, that would be 4, that would be 1/6. Okay, and then the z would be, if t were here minus 2, it really doesn't plus or minus 2, this would be 6 plus 4 would be 8 times 0. Yeah, z would be equal to 0. It would have to be. So that would be that. All right. This isn't working out well, is it? Well, let's see if there's some way they show it. Note that the k component implies that t is equal to, is between plus or minus 2. And that's what I was just trying to rationalize. You know, here z is 0 and there z is 0. And we're trying to figure out what the t would be. So if you looked at this, the z component here, and set that equal to 0, the only way that would be 0 is if 6 plus t squared times 4 minus t, yuck, I hate it when it does that, 4 minus t squared is equal to 0. Well, this thing's never going to be 0, ever. So this suggests that t is equal to plus or minus 2. So that's where we should have started. If t is plus or minus 2, then x is equal to t, so this would be um, so x would be going from plus or minus 2. Okay. And the y, which would be t squared, would be always positive. The y would be between 0, which is 0 right up there, less than or equal to y is less than or equal to 4. Okay. And then the z would be 0. Actually, it goes from 0 to 2. 0 less than or equal to z less than or equal to 2. Well, yeah, it can be equal to 2. So, so from the points 2, 4, 0 and negative 2, 4, 0, this would be x equal to, y is equal to 4, z is equal to 0, to over here, negative 2, 4, 0, and then this upper point here is 0, 0, 2. They don't mention that one. So that's what the trace looks like. And unfortunately, they don't show this on the PowerPoint, but I showed it to you, and that's what you got. So it's not a particularly, the drawing is terrible, but even the algebra calculations can be very tricky. Okay, so I think that ends example 4. Go to the, oh no, I was going to say go to larsonCalculus.com, but it's not listed there. Okay, so let me go back to screen sharing and go back to 12.1. All right, resume the slideshow, and where we go from here is limits and continuity. Now we worry about those, or used to worry about them, in scalar functions. They also are important in vector value functions. So here's the definition of the limits of a vector value function. If r, bold R here, I would draw it with an arrow over it, is a vector value function such that r of t is equal to f of ti plus g of tj. Now that on the plane, okay? Then the limit as t approaches a, some value a in its domain, t approaches a, of the limit of r of t is the limit of, as t approaches a, of f of t in the I direction, limit of g of t as t approaches a in the j direction. So what is that saying? The limit of a vector value function is the limits of the scalar functions in the I and j direction. That's if you're in the plane. Provided the f and g have limits as t approach a. That has to be true for that to be true. If r is a vector value function in 3 space, r of t is equal to f of ti plus g of tj plus h of tj, then the limit as t approaches a, this is talk about limits now, of r of t would be limit as t approaches a, f of t, and the I direction limit is t approaches a of g of t, in the j direction plus limit is t approaches a of h of t in the k direction. Provided, of course, that the f, g, and h do have limits as t approaches a. So basically, what we mean by the limits of a vector value function, as a t approaches some value, then let the scalar functions represented by that, in terms of that parameter t, they must also take the limit of them as t approaches a. That's assuming that they do have limits there. So if r of t approaches the vector L as t approaches A, then the length of the vector r of t minus L has to approach 0. Okay, that is the magnitude of the vector r of t minus L has to approach 0 as t approaches A. Now, I don't find this a particularly instructive graphic, but it is true. Okay, so here is your origin right there. There's the function L, or the vector L. Okay, here's your function r of t. Now, as t approaches A, then this function, the r of t, must get closer and closer to here. So as t is approaching A, as you're moving here, the difference between r and t and L, this is r of t down here, here's L here, so this is the difference here. As t approaches A, that gets shorter and shorter and shorter and shorter until it's exactly 0. The difference between r of t and L as t approaches A is approaching 0. Now, again, that illustration is absolutely correct, but it's just not all that obvious what they're getting at there, but that's what they're getting at. Okay? Now, the next definition extends the notion of continuity to a vector value function. Excuse me. Now, a vector value function r, there's a vector r, bold here. If I was drawing it, it'd have a vector over it. Okay, is continuous at a point given by t is equal to A when the limit of r of t exists as t approaches A, and not only does it exist, but it must be r of A. Okay, so it can't be that it does exist, but it's some value other than r of A. Won't work. Continuity means it has to be the same as r of A. A vector value function r is continuous on an interval I when it's continuous at every point in that interval. Okay, so this isn't a great illustration, but this is your curve here, and the r of A must be that point right there. Okay, because that would be pointing right there, and see, this is continuous. There are no gaps, no breaks or anything in that curve. As r is approaching A, then, and r is equal to, r of A is equal to that value. Okay, now here's example 5. This is over on page 824, near the top of the page. How we're doing on time. Okay. Discuss the continuity of the vector valued function r of t is equal to ti plus aj plus a squared minus t squared k, where a is some constant value. Okay, at t is equal to 0. Let's talk about the continuity there. Okay, now let's plug it in, if I can find my thing. Okay, so r of 0, that would be 0i plus aj plus a squared minus 0 squared, so that's just a squared k. Okay, that's supposed to be a 0 there. I can hardly read my own writing. Now, this is a vector here. Okay, so r of 0 is equal to aj plus a squared k, because this has a 0 component in I. Okay, now what can you say about that? That function is, I guess you would say, parabolic in A, but A is just a constant, so that's what it is. I don't know what else they want us to say. AJ plus A squared K. That's all that they had. Okay. Now, I think I'll erase my scratch here. Okay. So as T approaches 0, the limit is R of T would be the limit of T as T approaches 0, which would be 0I, plus the limit as J approaches 0 is limit of A as T approaches 0, which would just be A, plus the limit of A squared minus T squared as T approaches 0, just be A squared K, and that gives you AJ plus A squared K. No I dependence at all there. Okay. Now, because that's true, you can conclude that R is continuous at T is equal to 0. That there's no gaps, there's no breaks or anything there. That would be that R is continuous at T is equal to 0. Okay. By similar reasoning, you can conclude that the vector value function R is continuous at all real numbers of T, because there was nothing very special about A. That was just any real number. Now, for each value of A, the curve represents by the vector value function. Now this is the hard part. I'm so glad I didn't have to draw this. Okay. Now, AJ this is when A is equal to 0, you would have Ti plus 0J minus T squared K. Okay. So for any value A, this would be a parabola that's going opening downward. Okay. And these are those downward parabolas. There's A is equal to 0, A is equal to 2, minus 2, and 4 and minus 4. Okay. That is so for every value curve represented by some different value A, that's a parabola opening downward. You can think of the parabola as the intersection of the vertical plane y is equal to A with the hyperbolic paraboloid, and that's what you see here. Now, if you had done intersections this way, your parabola would have been going up in time. Okay. Like that one right there would have been, and then one over here would have been, and so on. Okay. Don't know specifically why they gave you that, but it's true. And there is one more example, so I guess I'll go back and let's do the last example. How are we doing on time? We've got a few minutes, so I think we can do it. Let's go to the whiteboard. Any questions before I clear any of this, or go back? We can go back to the previous one too. Okay. Determine the intervals on which the vectored value function R of T, if I could get my pen to write here, there we go, R as a function of T is equal to Ti plus the square root of T plus 1 J plus T squared plus 1. Yuck, this thing is so aggravating. T squared plus 1 k is continuous. Determine the intervals on which this vector value function is continuous. Well, every one of the scalar functions that make the components of that must be continuous. This t is continuous everywhere, polynomial. This is not, however. In this case, t plus 1 has to be greater than or equal to 0, meaning t is greater than or equal to minus 1. This one, good everywhere. Again, good old polynomial function. Okay? I did write it right, didn't I? Yes, I did. So, that's it says here, determine the intervals on which these vector value function is continuous. That's the interval right there. Minus 1 to infinity. It's continuous everywhere past minus 1. Any t greater than or equal to negative 1. Okay? So that's exactly how they wrote it as well. Alright. Negative 1 to infinity. That's the t values. Alright. Homework exercises here. Always take a look at the concept checks and see those. At least the odds should be at calcchat.com. I can't swear about the evens, but the odds should be. Then homework exercises, any of the odds 3 through 9, they should all be at CalcChat. 3 should be at CalcView. 11 should be both at CalcChat and CalcView. 13 and 15 should both be at CalcChat. 17 should be at CalcChat. I would try to do all 4 of 19 through 22. Okay, I know there's a couple of evens in there, but it's matching. You should be able to match those, but the answers for 19 and 21 are at back of the book and at CalcChat. 23, any of the odds 23 to 29 should be at CalcChat. 25 should be at CalcView. 31 through 37 should be at CalcChat. 31 should be at CalcView. 39 should be at CalcChat. 41 should be at CalcChat. Either 43 or 45 should be at CalcChat. Any of the odds 47 to 53 should be at CalcChat, with 51 being at CalcView. Any of the odds 55 through 61 should be at CalcChat, with 55 being at CalcView. 63 should be at CalcChat. 65 through 69 should be at CalcChat, with 67 at CalcView. 71 through 75 should be at CalcChat, with 71 at CalcView. 77 or 79 should be, well, let's see. I'd say any of the odds 77 through 85 should be at CalcChat. 87 should be at CalcChat. And 89 should be at CalcChat. There's an interesting section project there talking about the witch of Agnesi, which is such a corruption of what it should be. I can't think what her first name was, but Agnesi was a brilliant mathematician way early in mathematics, and she was a woman. Okay, her father, I think, was a professor, and she learned all that she could and was a brilliant mathematician long before women were even allowed to study anything, and she was ranked way up there. She came up with a curve, and her native language was Italian. I don't know if she wrote in Italian or in Latin, but one or the other. But then when they translated it a couple times, the curve of Agnesi became the witch of Agnesi. Now, I can't help but imagine they named it a witch just because she was a female, you know. So it's a terrible translation, and to this day that's still what they call it. All right, how are we doing on time? We've got 10 minutes, right? So let's move on to 12.2. There's 12.2. This time it showed up. Sometimes it doesn't, and I have to go and load it again. So let's go from current slide 12.2. All right, again, we're in Chapter 12, Vector Value Functions. This time we're in 12.2, Differentiation and Integration of Vector Value Functions. The two objectives are, first, differentiate a vector value function. Secondly, we'll integrate a vector value function. Okay? Now, how you do this, hopefully, is exactly what you would imagine it to be. Because of continuity and other things being the same, your differentiation and integration should be, I would hope, exactly what you thought it would be. The definition of a derivative of a vector value function parallels the definition for real valued functions, or scalar functions I like to call them. Okay? And that's this. The derivative of a vector value function, r, is, now that's the first derivative of r, how the vector function r is changing with respect to time. So that prime means with respect to the independent variable t. It doesn't have to be time, but t, okay? That would be the limit as of that r of t plus delta t minus r of t divided by delta t. Change of y over change of x, that should be your derivative. The limit is that delta t approaches 0. That would be the slope at the point, whatever that point t was, for all t's for which that limit exists. So if r prime of t exists, then r of t is differentiable at t. If r prime exists for all t on an open interval I, then r is differentiable on that interval I. Notice this open interval doesn't include the endpoints, just everything in between the endpoints. Differentiability of vector value functions can be extended to closed intervals, not just open, by considering one-sided limits. So you can do that just like we did in scalar derivatives. So differentiation of vector value functions can be done on a component by component basis. To see why that's true, let's consider this function r of t, some f of ti plus g of t j. Applying the definition of the derivative produces the following. R prime of t is the limit as delta t approaches 0 of r of t plus delta t minus r of t divided by delta t. So what we would do, this would be r of t plus delta t would be f of t plus delta t I plus g of t plus delta t j plus f of minus f of t I minus f of t j. That would be the limit as delta t approaches 0. And if you take this term and combine it with that term, r of t plus delta t I minus f of t plus delta t I minus f of t I plus g of t plus delta t j minus g of t j, then that limit would be the limit of your f of t plus delta t minus f of t divided by delta t. That would just be your first derivative of f. This would be your first derivative of g. So here's what it says. The derivative of a vector value function is the derivative of the I component scalar function I plus the derivative of the y scalar function as a function of tj, and extend that to free space, and then you would have a h prime of tj. So basically what you do, take the derivatives component by component, just like they say here. Okay, so here it is, and I think that important result is this theorem shown below. If r of t is equal f of ti plus g of tj in the plane, then where f, and why these vertical lines are sometimes show up, I don't know, where f and g are both differential functions of t, then the r prime of t is f prime of I plus g prime tj. And in space, if r is f of ti plus g of tj plus h of tk, where f, g, and h are all differentiable functions of t, they have to be. If they are, then r prime is f prime I plus g prime j plus h prime k, just like I hope you would expect them to be. All right. Note that the derivative of a vector value function r is itself a vector valued function, because you keep the I, j, and k right there. You can see from the figure that r prime is a vector tangent to the curve given by r of t and pointing in the direction of increasing t values. So if this is your curve right there, r prime, this is your r of t here at that point t, your r prime would be your difference between r prime plus delta t and r prime. So you see it's that difference minus that difference there, and that gives you basically the curve tangent to, the line tangent to the curve at that point. Okay, just what we would expect it hopefully to be. Here's example 1. All that was a lot of blah blah blah. I think you'll find these are pretty easy to do. Okay, for the vector value function r of t, if I could get the pen to show up, where are you, pen? There you are. R of t is equal to ti plus t squared plus 2j. Find r prime of t. Okay, well, r prime of t with the derivative of t would be 1, so that's I, plus 2t, derivative with respect to t is 2t plus 0, j. Okay, that would be r prime of t. Then sketch the plane curve. Oh boy, I knew this was coming. Plane curve represented by r of t and the graphs of r of 1 and r prime of 1. Okay, so let's see if we can get, this is a plane curve, so that makes it a little easier. I can't draw straight lines, but okay, there's your plane curve. Plane curve represented by r of t. So when t is equal to 0, this would be 0i plus 2j. So, okay, there would be your initial point there. Okay, when t is equal to 1, that would be 1 in the I direction, and 1 plus 2 is 3 in the j direction. So that would be somewhere up there. Okay, then when t is equal to, let's do negative 1, it would be a negative I, and that would still be a 3 in the j direction. So like this. So this appears to me to be a parabola whose vertex is there. I can't get my pen to come anywhere close to where I want it to go. Something like that. That's that parabola. Okay, I still can't get the pen to graph where I want it to. Okay, now sketch the plane curve represented by r of t. I think that's it. And the graphs of r of 1. Well, r of 1 would be right here. That would be an r prime of 1. Okay. So r of 1, I can't write, is equal to I plus 3j. Okay, so that would be 1 in the x direction, 3 in the j direction. So that would be something like that. R prime at 1 would be r prime of 1 would be I plus 2j. Okay, now this is kind of tough to distinguish here, but one of these would be sort of like that and one like that. Let's see if we can get them to show us, because my drawing is so lousy. Okay, so let's clear this. Differentiate on component by component basis to be I plus 2tj. From the position vector r of t, you can write the parametric equations. X is equal to t and y is equal to t squared plus 1, t squared plus 2. The corresponding rectangular equation would be y is equal to x squared plus 2. I don't know why they did this, but they did. That's correct though. Where t is equal to 1, r of t is equal to 1 plus 3i, r prime is 1 plus 2i, I plus 2i, and that would be a parabola there, drawn from the, starting at the origin. And I did draw this poorly. The r of 1 vector is from the origin to that point. That's 3 up for every 1 over, okay? And then this one, the r prime of t, is drawn tangent to that, and that's right 1 for every 2 up. And that's how I should have drawn it, but I was in a hurry and didn't quite get that right. But there's your parabola, basically about like we did it. I just couldn't get mine to draw very pretty, but it did just there at that. Your r of t is always drawn from the origin. The r prime is always drawn from the point of contact. Okay, so that's what we got. And your arrow here indicates increasing values of t, because remember this is that t is equal to -1, 0, +1, 2, 3, 4. So it's going around in that direction. Okay. Whoa, we've just gone 2 minutes over. Where are we in the text here? My pencil has gone somewhere way up there. Well, I don't even see where we are in the text. I think they've skipped example 2. Yeah. Okay, we'll pick up next time with example 2. See, we may have gotten enough done for homework exercises here. Let's see if we did. Not very many. I think you can do any of the odds 3 through 9. I think you can even do 11 through 17. Let's stop there and we'll pick up with the rest of those next time. Any questions? All right, remember, anyone who came in late, that there is no class on Wednesday because it's Veterans Day. So sorry about that, but get over it. And also, we will have class next week. Then Thanksgiving week, there's no class at all. And the week after Thanksgiving is our last week of class. And I'll give you your final exam on that last Wednesday, first Wednesday in December. And then you'll have the next week to turn it in. So running out of time here on the short rows, as we used to say down on the farm. And that means please get your research papers in. Please get your earlier test in, because we will have the final coming up pretty soon. Okay? Any questions? Be careful, be safe. The counts are just going through the roof as far as COVID goes, so be safe, people. It's not worth it. Take care. We'll see you on, well, I'll see at least one of you in about half an hour, and the others will see you next week. Take care. Oh, I can't get it to turn off. There it goes.